Hello everyone, my name is Minxue Tang, and welcome to this presentation. And it's my pleasure to introduce our work, ModelGuard Information-Theoretic Defense Against Model Extraction Attacks. So in this presentation, I will first introduce the background and the threat model for model extraction attacks. And based on the threat model, I will formulate the defense objective of our method as a constraint optimization problem. And then I will develop two variants of ModelGuard to solve the optimization problem under different assumptions. Finally, I will show the experiment results and summarize this presentation. So let me first introduce what is model extraction attack and how it is conducted. In a machine learning as a service system, there is usually a black box model, FT with the parameter WT and deployed in the server. And this target model will provide service for the users, and the users can query this target model with some query data and get predictions from it. And in model extraction attack, the attacker aims at stealing these parameters or functionality of this target model to a substitute model FS. And to this end, the attacker may use a query dataset XQ to query this target model and get predictions from it. Then the substitute model will be trained with the predictions from the target model. And the model extraction attack allows the attacker to bypass the charges for using the service. And furthermore, it can expose the vulnerability of the target model and enable very powerful downstream attacks, such as evasion attack or membership inference attacks. So to defend against the model extraction attack, different methods have been proposed, including extraction detection, model watermarking, or prediction perturbation. And in this work, we will mainly focus on the prediction perturbation, where the defender can use a perturbation mechanism P here to perturb the claim prediction and return the perturbed prediction to the users. And we also consider the attacker to be adaptive, so they will also try to use some recovery function R to try to recover the claim prediction from the perturbed prediction. And we consider two kinds of attacks here. The first kind is called the parameter stealing attack, where the attacker aims at minimize the difference between the substitute model and the target model. And the second kind is called the functionality stealing attack, where the attacker only care about the output similarity, and they will imitate the output of the target model with a substitute model. Namely, they will try to minimize the difference between the predictions. So given the threat model here, we can formulate our defense objective in the opposite to that of the attacker. Namely, we maximize the parameter difference to defend against the parameter stealing attack, and we can maximize the prediction difference to defend against the functionality stealing attack. However, we know that the attacker can use arbitrary training algorithm to train the substitute model. So the training algorithm here is unknown to the defender, so it will be intractable to directly maximize the parameter difference when defending against a parameter stealing attack. Fortunately, we have the following lemma 1 here, showing that if we can maximize the prediction difference, we can also maximize the lower bound of the parameter difference. So defending against the functionality stealing attack can also defend against the parameter stealing attack. Therefore, we will mainly focus on the functionality stealing attack in the following. So since perturbing the prediction can also influence the utility of the target model, so we also introduce these 3 different constraints to maintain the utility when solving the optimization problem, including the L1 distortion constraint, the top 1 accuracy preserving constraint, and the simplex constraint for classification validity. We now introduce how to solve the optimization problem about. And the challenge here is that the recovery function is still unknown to the defender, and it can be arbitrary as well. So we have to make different assumptions about this recovery, including the first assumption is that the attacker will not use the recovered mechanism at all, so they directly use the perturb prediction for training. And this will lead to our first variant, ModelGuard W. And in the second assumption, we assume that the attacker will use a very strong adaptive attack. Then the recovery function will try to minimize the recovered distance between the recovered prediction and the claim prediction. So this will lead to the second variant, ModelGuard S. So let me first introduce ModelGuard W. So with assumption 1, we know that the vacuum tilde is equal to vacuum hat and also with the cross-entry bylaws that is commonly used in classification tasks, we can get the left-hand side objective function here, where we will try to minimize the inner production between YQ, the clean prediction YQ, and log YQ hat. And we find that this is still difficult to solve because this function is in fact a non-convex function, and it's very difficult to solve it, to minimize it with the constraints here. So we just swap YQ and YQ hat, and we get the right-hand side optimization problem where we will minimize the inner production between log YQ and YQ hat. And this function is actually linear in the variable YQ hat, so we can solve it with linear programming. This will be much easier. And we also show these two problems have very similar solutions in the appendix of our paper. And now let me introduce the second variant, ModelGuard S, which defends against the strong adaptive attack that minimize the recovery distance in assumption 2. So our lemma 2 here shows that the recovery, for any recovery function R, we have a lower bound on the recovery distance as given follows. And the lower bound can be achieved by the Bayes attack that uses the Bayes estimator as the recovery function. This second variant, ModelGuard S, will try to maximize this lower bound. Namely, it is equivalent to minimize the mutual information between the clean prediction YQ and the perturb prediction YQ hat. And if you are familiar with information theory, you will find that this problem is exactly the rate distortion problem in information theory, and we can use some lossy compression method to solve this problem, such as the vector quantization. As the query usually comes into the machine learning as a service system sequentially, so we propose to use an online vector quantization method to achieve better performance. However, a problem here is that in the online quantization method, if there are more data comes in, more centroids will be created as in the figures. And in this case, the quantization boundary may change as more centroids are created. And as shown in the first row, if the quantization boundary changes, the attacker may get more information about the clean prediction. For example, if they query with this black point in the early stage, they will get a blue circle as the result. And if they quantize it in the late stage, they will again get a green point as the quantized result. And in this case, they will immediately know that this black point is near the boundary of this blue circle and the green circle. And they can get extra information about the clean prediction now. So to avoid this, we propose the ordered incremental prediction quantization, where we will remember all the creating order of all the centroids, and we will always quantize a prediction to the first centroid that lies in the distortion constraint. And as shown in the lower rows, if we create this blue point first, and if we query with black point, this black point will always be quantized to this blue point. And in this case, the quantization boundary of each centroid will never change. So now let me just show the experimental results to validate the effectiveness of ModelGuard. We conduct experiments on 4 different data sets, including Caltech 256, Cube 200, Cepha 100, and Cepha. And we conduct experiments against 2 attacks here. The first row shows the results of the naive attack, where the attacker will not use any recovery function. And in the second row, we evaluate against the Bayes attack, where the Bayes attack will minimize the recovery distance as we introduced before. And we could see that among all different baselines and our ModelGuard, the ModelGuard W can achieve the best result when defending against a naive attack, since it aligns with the assumption 1. But when we defend against the Bayes attack, which deviates from assumption 1 and aligns with assumption 2, ModelGuard S achieved the better result. And we find that the Bayes attack can always achieve the highest extraction accuracy than among all different attacks in our paper. So the Bayes attack is actually the extreme case, and it is worst case of our defense. So When we consider using which defense measure, we should always consider ModelGuard S, since we should always consider worst case in the defense. And we also show the relationship between the mutual information and the recovery distance. When defending with different distortion constraints in ModelGuard S, the total number of centroids will also change. In general, more centroids imply higher mutual information between the clean prediction and the perturb prediction. And we can see in the first row here that with more centroids, the recovery distance will decrease as the right line, and the extraction accuracy will increase. This also aligns with our lemma 2. And we also show the response time of different defense measures at the bottom. And we can see that the ModelGuard S almost introduced no extra computation time compared with no defense, none here. So this means that the ModelGuard S can also satisfy the real-time requirement in machine learning as a service systems. Okay, now let me summarize this presentation. We develop a general framework for model extraction attacks and defenses covering two kinds of attacks, the parameter stealing attack and the functionality stealing attack. And we propose a unified defense objective against both attacks. Then we propose two variants of ModelGuard to solve this constraint optimization problem in the defense objective. Finally, we show the superiority of ModelGuard by experiments in different datasets against different attack measures. And this is the end of the presentation. Thank you, and welcome to asking me any questions.